So the topic is Astable Multivibrator. Now as we came across the Monostable Multivibrator in our last class, so the difference between an Astable Multivibrator and a Monostable Multivibrator, okay, let's define what is an Astable Multivibrator first, then we will go through the difference between the Astable and the Monostable Multivibrator. Now in an astable multivibrator, there are no stable states at all. So for an astable multivibrator, the wave pulse, or rather the output waveform, is like a wave train and it will go on continuation. So for an astable multivibrator, there is no stable state, whereas for an monostable multivibrator, which we have discussed in our last class, as we know that there are only one stable state. So forget about the monostable multivibrator and now focus on this astable multivibrator. What are the difference between an astable multivibrator and a monostable multivibrator? Let's discuss it first. Now as per the circuit construction is required for an astable multivibrator, you will require no trigger input. You will require, or rather we will require no trigger input for an astable multivibrator to operate. So that's the difference, that's a main difference between a monostable and an astable multivibrator. Now here also there are some differences. One difference is that here two resistors are connected, R1 and R2. These are R1 and R2. So these R1 and R2, that is two resistors, are externally connected to the circuit, whereas as we know that for a monostable multivibrator there remains only one resistor, one capacitor. Here capacitor is the number of capacitor connected is 1 also, but the difference is here there are two resistors, R1 and R2, connected externally with this circuit. So that's a difference. And the other difference is that now here as you can see that pin number 6 and pin number 2, these two pins are shorted. These two pins are shorted or connected with each other externally. So that's also a difference between a monostable circuit and an astable circuit. So these are the differences, but now let's focus on how the circuit operates. How the circuit operates, or what is the circuit operation, let's discuss it first. So these are the differences between an astable and a monostable circuit. So let's consider that initially when the circuit is switched on, first of all, the circuit is switched on, that is the power supply is switched on. So what happens when the power supply is switched on to this circuit? The capacitor C, here you will find two capacitors. These two capacitors are also presented in the monostable circuit, especially this capacitor, that is the value of 0.01 microfarad capacitor, and that is the capacitor which is connected with the control input, that is pin number 5. So pin number 5 is connected with a capacitor of value 0.01 microfarad and to the ground. Now the circuit operation looks like this, or you can explain this as the circuit is switched on, the capacitor C momentarily acts as a short circuit to the ground. The capacitor C momentarily acts as a short circuit to ground, and the timer is triggered as the capacitor is connected to the trigger pin. We can see here that the capacitor C is connected with pin number 2 as well as pin number 6. So here when the circuit is switched on, the capacitor momentarily is connected to the ground. As the capacitor is connected to the ground, so it actually acts as a short circuit to ground, and the timer is triggered as the capacitor. Now because pin number 2, what was pin number 2? from our block diagram or internal structure, we can easily say that pin number 2, I also mentioned here that pin number 2 is the trigger input, pin number 6 is the threshold input. Now these two inputs are connected with each other, and that is connected to the capacitor itself. So as the circuit is or the power supply is switched on, the capacitor C momentarily acts as short circuit to ground, and the timer is triggered as the capacitor is connected to the trigger pin. Now, what will be the output? What will be the output at this particular time? The output of the timer becomes high. Why the output of the timer becomes high? As in our previous lecture, that is in the lecture of monostable multivibrator, as well as when we have discussed about the 555 timer as a whole, we have discussed that when the trigger comparator output is high, rather when the trigger pin goes below VCC by 3, when the trigger pin goes below VCC by 3, the output of the timer is high. So when the trigger input goes below 1/3 of VCC, the output of the 555 timer goes above or rather goes to the high state. So here what I have just explained, that whenever the circuit is switched on, this is the VCC or this is the power supply which is connected for this circuit. Now whenever this circuit is switched on, what the pin number 2 gets, as if we assume that the capacitor is initially discharged, that is the charge inside the capacitor is 0 at time t equals to 0. So that is the assumption we are using here. Now as the circuit is switched on, the capacitor is initially shorted to ground, and that is the value. So the value of the voltage at the capacitor, if the value of the voltage at the capacitor is 0, that means it is lower, it is smaller than the value 1/3 of VCC. Now as we know from our discussion on internal structure of 555 timer, that whenever the trigger input goes below 1/3 of VCC, the trigger comparator goes high. And that will help the set input of the RS flip-flop goes high, which actually makes the output of the 555 timer, or rather which makes the Q output of the flip-flop goes high. That means Q bar goes low, and after the output buffer from which the output of the 555 timer goes, so the output of the 555 timer will also be high. So that is the initial state which I have discussed now. That is, whenever the circuit is switched on, whenever the power supply is on, that will make the capacitor is connected to ground, and it will help the trigger input goes below the value of 1/3 VCC. It will make the trigger input goes below the 1/3 VCC, and that will make the output of the 555 timer goes high. Is it okay? So the initial stage, at the initial stage, whenever this circuit is switched on, the output of the 555 timer, or rather the output of this particular circuit goes high. Is it okay? Is it okay? Okay. So now proceeding further, that what we have learned that at the initial stage of the circuit, at time t equals to 0, when the circuit is switched on, the 555 timer output is high. Now as the output goes high, so that means the RS flip-flop output Q is also high. Now as Q is high, that will make the Q bar output low. Now Q bar is the complementary output of the RS flip-flop inside this 555 timer IC. You all know that. So as Q is high, that will make the output, or that will make the value of the Q bar goes low. Now the Q bar output, we all know that the Q bar output is connected to the base of the discharge transistor Q1. Have you all remembered this? That the Q bar output is actually connected to the base of the Q1 transistor, that is the discharge transistor. And as we all know that when the transistor input or the base input is low, that will make the Q1 transistor operating in the cutoff region of its output characteristics. So whenever the circuit is switched on, I am again continuing with this, that whenever the circuit is switched on, the capacitor momentarily connected to ground, and that will make the trigger input goes below the value of 1/3 VCC, which actually sets, or rather which actually makes the trigger comparator output goes high. And then if the trigger comparator goes high, which is actually connected to the set input of the RS flip-flop, so that will make the set input goes high. Now as the set input goes high, that will make the output Q of the SR flip-flop goes high. So as the output of the SR flip-flop goes high, that will make the Q bar output of the SR flip-flop goes low. As Q bar output is 0, or rather Q bar output is low, which is also connected to an output buffer and with the base of the discharge transistor Q1. So that will make the transistor Q1 operating in the cutoff region, right? So now if the transistor is in the cutoff region, that will ensure that the capacitor is actually isolated, so the discharge pin is actually isolated. So the discharge pin is actually practical, or rather precisely we should tell that the discharge transistor, or rather the discharge pin, that is pin number 7. Pin number 7 is actually disconnected, but this disconnection is more precisely, we should mention that this disconnection of the discharge pin is happened practically. It happened practically. So the discharge pin, that is pin number 7. Pin number 7 is practically isolated or practically disconnected. So as pin number 7 is practically isolated, what will happen? So the capacitor begins to charge towards VCC. As the pin number 7 is practically isolated from the ground, that will make the capacitor begins to charge towards VCC. So now onwards, as the pin number 7 is practically isolated or practically disconnected from this circuit, so that will make the capacitor C to charge towards the value of VCC via these two resistors R1 and R2. So now as on the capacitor is charging towards the value of VCC through the resistors R1 and R2, that will make the time constant of charging will be depending upon the value of R1 plus R2 into C. not only RC, but the value will be R1 plus R2 into C. So the resistance will be R1 plus R2, that is the series resistance, as these two resistors are connected with each other. So the time constant of charging of the capacitor C will be R1 plus R2 into C. Okay? Is it okay? Fine. So now at this particular point, what we have explained, so repeating again, now at this particular time we have explained that initially when the circuit is switched on, the output of the 555 timer goes high, and that will make the discharge pin, that is pin number 7, isolated from ground. Initially the capacitor was initially shorted to ground. Now as the output voltage is high, the output voltage of the 555 timer is high, it will make the discharge pin isolated from ground, or rather disconnected from ground. So now the capacitor C, it can see the value of the voltage VCC here. So now the capacitor can be charged. Now the capacitor will go on charging. Now as the path in which the capacitor goes to charge, the circuit or the path comprises of these two resistors R1 and R2, which are in series. So the time constant of charging of this capacitor C will be R1 plus R2 into C. Okay. Now the capacitor goes on charging. What will happen? Again case 2, or rather part 2 of this explanation. Now when the capacitor goes on charging, let us assume it is go on charging from the value of 0, as because initially the capacitor was discharged, or initially the capacitor has a value of 0 volts. So the capacitor will move from 0 to the value of VCC, or to the value of 5 volts. Now as it moves forward, as it goes on charging, so one time will appear when the capacitor voltage goes beyond the value of 2/3 VCC. 2/3 VCC, as we all know, that 2/3 VCC means approximately 3.33 or rather 3.4 volts. So as the capacitor has a value of 3.3 or 3.4 volts, that is nearly equals to 2/3 VCC or beyond the value of 2/3 VCC, what will happen? Look at the circuit. The capacitor is connected to the trigger as well as to the threshold pin, that is pin number 6. Now as we have already discussed in our first class, when we have discussed about the internal structure of the 555 timer, we have encountered that when the threshold input goes beyond 2/3 VCC, when the threshold input goes beyond 2/3 VCC, it will make the threshold comparator output goes high. When the threshold input, that is pin number 7 goes, when the threshold input, that is pin number 6, goes high, it will make the threshold comparator output goes high. So when the threshold comparator output goes high, what happens? The the reset input, that is the R input of the SR flip-flop, the R input or the reset input of the SR flip-flop goes high. As we all know that for an SR flip-flop, if the reset input goes high, it will make the Q output goes low. So the Q output goes low, that means Q bar goes high, that means the output buffer goes low. That means the timer output, now the timer output goes low. When the timer output goes low, initially the timer output was at its high state. Now as the timer output is high, the capacitor goes to charge. Now when the capacitor voltage or the capacitor value equals to 2/3 VCC. So here we can see a graph. Here we can see the capacitor is charging via the time constant R1 plus R2 into C, and when the capacitor voltage reaches the value of 2/3 VCC, as because this value or the capacitor is connected to the threshold or pin number 6. So as because the capacitor voltage or VCC touches 2/3 VCC, it will make the output of the comparator goes low. So now if we draw up to this part of explanation into the waveform, what we can see. So I am drawing this output of the Astable multivibrator. Let us first draw the capacitor value. So here it is the capacitor voltage, and this is the output of the comparator. This is the output of the output of the 555 timer or output of this Astable multivibrator. So as because say this is time t with time. So as the capacitor, let it be 2/3 of VCC, and this is the value of the voltage VCC. Now as initially what we have discussed, that initially when the circuit is switched on, the output is literally in its high state. So the output is literally in its high state. Now as the output is high, the capacitor, as the output goes high, the capacitor starts to charge. So the capacitor starts to charge, and this charging will be up to this value of VCC, But you can see that at this particular point, when the capacitor reaches the value of 2/3 VCC, what will happen, as this capacitor is connected to this threshold pin? I am repeating again and again. Have you any discrepancies? Please mention here. I will tell you again. No problem, that is. But you should get this explanation clear, crystal clear. So as the capacitor charges, it will go up to the value of, it will try to charge up to the value of VCC, but when the capacitor voltage reaches 2/3 of VCC, as it is connected to the threshold pin, the threshold comparator goes high. The threshold comparator goes high, so the reset input of the RS flip-flop goes high, and as the reset input goes high, the flip-flop output, that is Q output, goes low, Q bar output goes high, and after the output buffer, the output of the comparator goes low. So when the capacitor reaches the value of 2/3 VCC, the output of the comparator goes low. The output of the comparator goes low. Okay. Now as Q goes high, as Q, that is the output of the that is output of the SR flip-flop goes low. When the capacitor value reaches 2/3 VCC, the output of the RS flip-flop goes low. As the Q output or the RS flip-flop output goes low, it will in turn make the Q bar, that is the complementary output of the RS flip-flop, goes high. Now again, when the RS flip-flop output or the complementary output, that is Q bar of the SR flip-flop goes high, as this output is connected to the discharge transistor, that is transistor Q1. So the transistor will be in its saturation mode, and as a result the capacitor is again shorted to ground. Again the capacitor C, which was charging, as the output voltage reaches 2/3 VCC, now the capacitor is again shorted to ground, and that will result in that the capacitor now from the value of 2/3 VCC, it will starts to discharge. Now as it is discharging, what will be, now the question is, what will be the time constant of discharge? Just look at the circuit and you will be intelligent enough to answer this question. That's what is the time constant of discharging. Look at this part of the circuit. Now initially when the capacitor was charged, the capacitor is charging through this path of R1 R2. Now as the value of the capacitor reaches 2/3 VCC, it will initiate the output of the 555 timer goes low. Now as the output of the 555 timer goes low, it will allow, or rather it will make the discharge pin shorted to ground. So that will make the capacitor to discharge, and now the path of discharging is only R2 via the resistor R2, as because R1 is disconnected to the upward part of the circuit, and the capacitor and the pin number 7 and the capacitor is actually shorted to ground. So the capacitor will be discharged and the discharging time constant will be R2C. Is it okay? Have you got it? Why the time constant of the discharging of this capacitor is R2 into C, and the charging time constant was R1 plus R2 into C. So the time constants of charging and discharging are dissimilar, are not equal. So the time constant or the charging time constant as R1 plus R2 into C. So here I mentioned this in this part of the graph, that the time constant is R1 plus R2 into C. So this is R1 plus R2 into C, and when the capacitor starts to discharge, the charging slope and the discharging slopes are different, as because the discharging time constant is different, and that is R2 into C. So here the capacitor will be discharge more faster, and it will go on to the value of 0 volts sooner. Now but as it will move to discharge, or it will move to the value of 0 volts. Up to this, is it clear? Is it clear? Is it clear for you up to this part of this lecture, that now the capacitor starts to discharge from the value of 2/3 VCC? Is it okay? Okay. So now as the capacitor starts to discharge via the time constant R2C, again we have a value of 1/3 of VCC. Say this is the value 1/3 of VCC. 1/3 of VCC means 1.6, rather 1.7 volts. Now the capacitor move on discharging, goes on discharging from the value of 3.4 or rather 3.5 volts. Now it will goes on decreasing. Now as it reaches as it reaches to the value of 1.7 or 1.8 volts, that is the value of 1/3 VCC. Now remember again what we have discussed in our first lecture of 555 timer, that as the value of the trigger input, goes below 1/3 VCC. So when this capacitor value goes below the value of 1/3 VCC, that is say 1.7. If 1/3 VCC is 1.7, then when the capacitor input, or rather the capacitor voltage, goes below 1.7, say for 1.5 volts of value, then what happens? So if this is the point, or this is the value of 1/3 VCC. So when the capacitor goes below 1/3 VCC, as we all know from this circuit, that the trigger input is also connected to this capacitor. So as the capacitor voltage goes below the 1/3 VCC, that will make the trigger input value goes below 1/3 VCC. So as the trigger input value goes below 1/3 VCC, what will happen? It will be similar. It will act as before. That is, as the value of the trigger input goes below 1/3 VCC, it will make the output of the trigger comparator goes high. It will again make the output of the trigger comparator goes high, and as the trigger comparator output is connected to the set input of the SR flip-flop, it will make the SR flip-flop output, that is Q of the SR flip-flop goes high. That means again Q bar is low, and after the output buffer, the output will be high. So now again, when the capacitor value touches the particular value of 1/3 VCC, I have marked here. So again, when the capacitor touches the value of 1/3 VCC, the output of the comparator now again goes high. So the output of the comparator goes high. And as we have already discussed in this particular lecture, that as the output of the comparator goes low, that means Q bar is high. So that will make the transistor Q1 in its Q1 as the output of the circuit, that is 555 timer, goes high, it will make the value of the Q bar goes low, and as this Q bar is connected to the transistor Q1, or rather the discharge transistor Q1 internally, so the transistor Q1 will be in cutoff state. So now as the output goes high, of the circuit, that makes the Q bar output goes low. As the Q bar goes low, that will make the discharge transistor in its cutoff state, and that will make the capacitor to disconnected. That will make the capacitor to disconnected from the ground. So now again a new charging cycle starts. So now again from this value again the capacitor goes on charging. So from this particular point again the capacitor goes on charging with this particular time constant R1 plus R2 into C, and now again and again as it reaches the value of 2/3 VCC, it will start to discharge. So this is the value, or this is the width of the high state. Now as the output goes high, again similar cycles repeats itself. So this is the particular waveform. So it will again in low state, and then it repeats again and again. So here this is the complete waveform. This is the complete waveform of an astable multivibrator by using a 555 timer. Now, as in the initial part of this particular lecture, I have mentioned that as the multivibrator is an astable one, we can't control when the value of the output, or rather when the value of the 555 timer output goes high, and when will it changes or it will move to the low state, as because there is no externally trigger value applied to this circuit. There will be no trigger value externally applied to the circuit, as there was a trigger input in the monostable multivibrator circuit. So here we can't make this circuit to happen that now you will move on to the high state, or now it will move on to the low state. This cannot be made. But we can make this transition, or we can make this width of this, we can change this width of the charging as well as the discharging time, as well as the discharging time of the capacitor, since because the charging time constant, as I have mentioned, that the charging time constant is R1 plus R2C, and the discharging time constant is R2C. So the charging time and the discharging time are dissimilar, are not equal. So the charging and the discharging times are dissimilar, and these time constants, that is either the charging or the discharging time constant, are actually dependent on the externally connected resistors. Externally connected resistors R1 and R2. So by changing the values of R1 and R2, we can change the time constants of charging or discharging. So that will in effect make the width of the high state or the low state. That can change the width of the high state or the low state of the output waveform. So that can be made. And in the following part, in the next part of this lecture, I will show you that is how the width can be changed, or rather what is the frequency of the waveform generated here. Now again the question is, have you any questions? Have you any doubt up to this mention? Have you any doubts? If you have any doubts, please mention, or rather I will move forward. Have you all understand the waveform of this 555 timer, or the waveform of this astable multivibrator circuit? Is it okay? Then I will move forward to calculate the time constant, to calculate the width of the output wave. No doubt. Okay, Dipanjan tells that no doubt. So now I can move forward. So remember that as the time constants are different, as the charging and discharging times are different, so here we should calculate the values that is we have to calculate the high time, that is the high time period as well as the low time period in different part. So let's first calculate, that is calculate the value of high time, that is TH. Let it be TH and the low time is TL. So first calculate the value, calculate TH, that is the high time period. Now as we all know that this high time period is dependent on the charging time of the capacitor. It depends on the charging time of the capacitor, and the charging time constant is nothing but R1 plus R2 into C. Again by taking the capacitor voltage at any time, the expression of the capacitor voltage for any time, that is VCT. So again, considering this expression of the capacitor voltage, that is VCT equals to the final voltage plus the initial minus the final voltage into e to the power minus of T by RC. So this is the general expression what we are going to use here for the two cases. Now here VI is the initial voltage of the capacitor, that is the capacitor voltage when time t equals to 0. So here and VF is the final voltage, that is the capacitor voltage when time t equals to infinity. Now as we are considering the case of charging, so during charging the initial voltage is 1/3 VCC. You will just see from this particular graph, though there may be a confusion that while considering the value of the initial voltage, that is VI, this value that is at time t equals to 0, VI is capacitor value when time t is 0. Okay, so that is the value, and as we can see that for the first part, for the first wave, we see that the capacitor starts charging from the value of 0 volts. So there is a confusion, there may be a confusion arises that for time t equals to 0, initial voltage is 0, but that is not the case, as because when this cycle repeats itself, when the waveform repeats itself, every time the capacitor starts to charge when the initial voltage is 1/3 of VCC. When the initial voltage is 1/3 of VCC, from this particular point, every time the capacitor goes to charge. So what will be our value? The initial value, it will be 1/3 of VCC. Is it okay? Why have I considered the value VI equals to 1/3 of VCC, not the value of 0 volts? As because every time, though the capacitor starts charging from the value of 0 volts for the initial part for the first time, but after this, when the cycle continues, every time the capacitor starts to charge from the value of 1/3 of VCC. Is it okay? So I have considered VI equals to 1/3 of VCC, right? Now let's move on to discuss what will be the value of VF. What will be the value of VF? VF will be, as I have told, that what is VF? That is the final voltage. When time t equals to infinity. Now when the time goes to infinity, the final value of the capacitor should be VCC. So the final value of the capacitor should be VCC if the circuit is operated for a time of t equals to infinity. So it will be VCC. Now let's put these values in this particular form. One thing, this is R and this is nothing but the charging, that is the time constant. So what is the value of time constant here? We have already mentioned, we have already known the fact that here for the charging part, the time constant is R1 plus R2 into C. So putting the value of R here for in this general expression, putting the value of R as R1 plus R2. Okay, so at time t equals to th, what is the value of VCT? VCT at time t equals to th, that is at this particular time, high time, the capacitor voltage is nothing but 2/3 VCC. So the capacitor voltage is 2/3 VCC. So let's put these values. Let's put these values in this expression. So we get 2/3 of VCC equals to final value, that is nothing but VCC plus initial value, that is 1/3 of VCC minus the final value, that is VCC, and then e to the power minus of t. T means th. I am omitting this V0 as it will confuse. So T means th divided by RC, that is R1 plus R2 into C. So this is the expression after putting the different values here. We can easily write 2/3 equals to 1 plus 1/3 minus 1, 1/3 minus 1, that is 1 minus 3 by 3, that is minus of 2/3 e to the power minus of th by R1 plus R2 into C. So here the value will be 1/3 minus 1, yes, the value will be 2/3 of e to the power minus of th by R1 plus R2 into C, and that is 1 minus of 2/3, that is 1/3. So cancelling this 3, we can get e to the power minus of th by R1 plus R2 into C, that equals to half. Okay. Now taking the logarithm or the natural log both sides, we will get th R1 plus R2 into C. We will get what we will get, taking log, we get th, or rather minus of th by R1 plus R2 into C. It will be ln half. Now ln half means ln1 means 0 and then minus of ln2. So there the value will be minus of ln2. We can cancel out these values of minus, and then we have th equals to R1 plus R2 into C into ln2. So that is the high time period, or the value of th, that is equals to R1 plus R2 into C into ln2. So this is the value of high time period. As we can see that here the high time period is actually dependent on the external components of this circuit, that is, it is dependent on the value of R1, the value of R2 and the value of C. So the entire time period or the high time period is solely dependent on the external components used in this circuit. Is it okay? Have you all have you any doubts up to this? How to derive? Have you all understand how we can find the value of th? If it's okay, let's move on to calculate the value of the discharging time or the value of TL. Okay. So let's move on to calculate the value of TL. Now for this, again, we have to consider this particular expression. So again, considering the general expression for charging and discharging of the capacitor, expression, here just no problem. Okay. So here now we are going to calculate the value of TL. Now here we should maintain that the initial value, that is the value of VI. What is the initial value when the capacitor starts to discharge? So during discharging, the initial value is nothing but 2/3 of VCC. So here the initial value is 2/3 of VCC, right? The final value, again the final value will be 0. So the final value will be 0. The capacitor will like to go to the value of 0 volts, but at any time, or rather at the time TL, but at the time of TL, the capacitor value should be 1/3 of VCC. So at T equals to TL, that is the low time, the capacitor voltage is 1/3 of VCC, from which again the charging path starts. So therefore we can write the capacitor value as 1/3 of VCC, that equals to final value is 0 plus initial value 2/3 of VCC minus the final value of 0, and now T will be TL. And now the charging, or rather the discharging time constant, here the discharging time constant, as we all know now that the discharging time constant is R2 into C. Okay, so just simplifying this, that is 1/3 VCC equals to 2/3 of VCC into e to the power minus of TL by R2C. So cancelling 3 and VCC, so we have half equals to e to the power minus of TL by R2C. Again taking logarithm in both sides, we have minus of TL by R2C, that equals to ln of half. That will make ln1 means again 0, that will be equals to minus of ln2. So again cancelling that negative value, we have the low time equals to R2C into ln2. So the value of TL is equals to R2C into ln2, and the value of TH was TH equals to R1 plus R2C into ln2. Okay, so we find out both the values of TH and TL. I think all you can understand how to calculate the value of TL. So now we will move on to calculate, that is our final destination. That is the destination in this particular lecture, that we have to find out the time period of oscillation. We have to find out the time period of oscillation, as because now we have the values of TH as well as the value of TL in our hand. So just by adding both these values, that is the value of TH and TL, we can find out the total time value, or the total time period. So to calculate the frequency of oscillation, we have to calculate first the time period, that is nothing but TH plus TL. We have the value of TH in our hand as R1 plus R2, as R1 plus R2C ln2, and the value of TL as R2C ln2. Okay, so C ln2, if we make common C ln2, we have R1 plus R2 plus R2. So that will make R1 plus 2R2 into C ln 2. So this is the total time period, or the total time period, that is the high time plus the low time. So what will the frequency of oscillation? It is just 1 by T, or that is 1 by R1 plus 2 R2 into ln into C. Oh, sorry. Into C into ln 2. So that is the frequency of oscillation for an astable multivibrator. And if we find out the value of ln 2, so just putting the value of 1 by ln 2, we have 1.44. It is approximated as 1.44 divided by R1 plus 2 R2 into C, and that is certainly in hertz. So this is the frequency of oscillation for an astable multivibrator. Okay? Okay. So last thing for this lecture, to conclude, we have another parameter to be calculated, that is known as the duty cycle. That is the duty cycle, or capital D. It is expressed as, or it can be written as, for any waveform generator circuit, the duty cycle is calculated, and duty cycle can be calculated as TH divided by TH plus TL. So just you have to put these values of TH and TL calculated in this particular lecture, and you will find the duty cycle of the waveform, or duty cycle of an astable multivibrator. As we can see that if we put these values of TH and TL, the duty cycle will be, always remember that duty cycle is also expressed in percentage. So duty cycle is TH means R1 plus R2 into C ln 2 divided by TH plus TL. TH plus TL means R1 plus 2R2 into C ln 2. Just cancelling these values, we have R1 plus R2 divided by R1 plus 2R2 into 100%. So it is a fractional value, it is a percentage value we always get. Now let us assume one interesting part to discuss with you, that let us assume that we want to make this waveform as a square wave. We want to make this waveform looks like a square wave. This is not look like a square wave, it is actually a rectangular waveform. So we want to find, or we want to get a square wave form from this astable multivibrator circuit. Now from the duty cycle viewpoint, what will be the values of high time and low time if the waveform is a square? If the waveform is a square wave, we can easily tell that the high time as well as the low time will be equal. TH and TL will be equal. So for a duty cycle of, so the duty cycle will be if the high time divided by, if high time and low time are equal, so the duty cycle will be half, or rather half into 100%, that is 50%. So 50% duty cycle means that the wave is nothing but a square wave, right? So what we will get if to make a square wave output waveform, to make a square wave, we have to make this duty cycle equals to 50%, that is half. So by putting the values of R1, so now as we are going to find a waveform looks like a 50% or looks like a square wave. We first find out these values of R1 and R2. Without finding these values of R1 and R2, we can't construct this particular astable multivibrator circuit. So to get the square wave output, we must calculate these values of R1 and R2, and then after following this particular circuit construction, we can easily make the square wave output. So we are going to calculate these values first. So R1 plus R2 by R1 plus 2R2 will be equals to 50%, that is nothing but half. So now simplifying, what we can get, 2R1 plus 2R2, it is equals to R1 plus 2R2, right? Now we have 2R2 both sides. So cancelling this 2R2, we have R1 equals to 0. R1 equals to 0. So that means to make a square wave output, from an astable multivibrator circuit by maintaining or by obeying this particular formula of duty cycle, we obtain a value of R1 equals to 0. That means we have not to connect any value of resistor as R1 here in this circuit, right? Now for an astable multivibrator, every time we have to connect two values of resistors. You can tell them as RA, RB, R1, R2, whatever may be, but there must be two resistances. But for the waveform looks like a square wave, what we have find that R1 should be 0. So now if we put the value of R1 equals to 0, that means we have to just connect a short as in the circuit of this astable multivibrator, and that will be not a astable multivibrator circuit. That will not be an astable multivibrator circuit. So the conclusion is, from an astable multivibrator circuit, we can't get a square wave. We can't get a square wave waveform for this simple astable multivibrator circuit. But is it right? Is it right that we can't get a square wave output waveform from an astable multivibrator? Yes, it is right, but this can be made by adjusting some circuit components, but that is not your scope of understanding, or that is not your scope of syllabus to discuss. So here in this particular lecture, what we have obtained, we have learned that what is an astable multivibrator circuit, what is the circuit of operation, how the circuit is operated, what the waveforms looks like, how to calculate the high time and the low time, as well as the frequency of oscillation for an astable multivibrator, and later what is the duty cycle and how we can't make a square wave, simple square wave output from a simple astable multivibrator circuit, right? So we have concluded everything about the 555 timer circuit. We have discussed the basics of 555 timer in our lecture 1. Lecture 2 comprises of the monostable multivibrator, and in this particular lecture we have discussed about the astable multivibrator circuit. So is it okay? Till then, goodbye.